So with that, I'll take some questions. Yeah?
So you include the full band treatment, so
yeah.
in this way you have a more realistic inspection. Another way, you can also do the incoherence cutting. So my question is...
what cutting?
Incoherent, inelastic cutting.
Yeah.
So my question is, how does the full band inclusion affect the electron phonon coupling? So maybe you also, I don't know if you include also the momentum dependent on the electron phonon coupling, it's more difficult to handle.
So this wasn't covered in this presentation really, and I would say this is undergoing current research where in the new Ullmann code that we're building, we are doing coupling, a full band transport with phonons and scattering. In NEMO 1D, we actually had two big buckets. We had scattering in single band, and we could do probably the most sophisticated scattering calculations that were out there in single band. And we always, to get the peaks right, etc., we had to futz with the effective masses because of the reasons that I showed, that it's a shortcoming of the effective mass theory. But we didn't have the compute power to include full band with scattering. We are reaching the stage now where we can do that. And we're doing that in my research group. And there's two ways of doing that coupling from phonons to the electrons. You can do the normal deformation potential way, or what we're doing in the new code, Mathieu Loisier coded this up, is where you actually look at the real crystal deformations in an atomistic representation and couple that into the Hamiltonian that is dependent on the atom positions. And you do that through direct coupling. So you compute the real phonon modes, let them deform the lattice, and you do a perturbation on that deformed lattice, not even deformation potentials.
Is it tight binding for phonons?
Yeah, well, it's tight. The phonons are kind of like tight binding with a valence force field, so balls on a spring. And once you know how they like to move on a ball on a spring, you can translate that into deformations that the electrons would see if these balls on the spring were to move. So it's the VFF coupled to tight binding, and that fluctuates the potential. And I can make a lecture of that tomorrow on what we do there. Okay? Any other questions? Yeah.
You did not mention the band-to-band tunneling mechanism. I mean between valence band and conduction band.
Wonderful question. Wait till tomorrow.
Okay.
Yeah, I will talk about it tomorrow. Okay? Everything clear as mud otherwise?